few more folks. Rob Parks, and I will be your MC for tonight's Evening Under the Stars. Yeah, completely just lost where I was going with that. All right. Tonight, what the agenda for tonight is that we're going to have a speaker give a public talk. Tonight, we're going to be we are going to be honored with the presence of William Matzko, a graduate student here at George Mason, and he will be talking about colliding galaxies. After his talk, we will be moving on to the telescope portion of this evening. Unfortunately, the weather is not cooperating with us, so we will be giving a closed dome tour. We will be showing you images like the ones you see on your screen of objects that we've taken in the past. And these images are primarily taken by our undergraduate students who are members of the Friends of the Observatory. And so the way that we take these images are essentially, let me say that, well, let me back up a little bit and point out where our observatory is. Our observatory is located on Research Hall on the Silver Tower, which you may have noticed in the past. The control room is on the roof of Research Hall itself. And prior to the pandemic, the telescope was operated from that control room exclusively. But because of the pandemic and the shutdowns, it accelerated our plans to make the telescope remote. And so at this point, if you have an internet connection and the right permissions, you can use this telescope anywhere you'd like. And frequently we have students who sit in the comfort of their own homes and actually use it for data collection. As I said, this is the Evening Under the Stars. Typically, this is the last event of the spring semester. We have been doing this over the course of the spring semester over alternating Tuesdays and evenings. This summer, we will be taking a break, and then we will be recommencing with this series come fall. Dates or the particular days to be announced. As I mentioned, it starts off with a 45-minute public talk appropriate for all ages, and then afterward, a 30-minute guided tour. If you are interested in the events or the activities surrounding our observatory, I highly suggest or highly encourage you to sign up for the Moon or the Mason Observatory Outreach newsletter. Within that newsletter, we talk about public events that you can participate in, primarily hosted by the Astronomy Club in Virginia, the Northern Virginia Astronomy Club, NOVAC. Along with this, we have M highlights a constellation of the month. I talk about space news, whatever is happening in space exploration or research that is particularly of interest. And then we also highlight students who are doing active research within our department, among other things. So if you are interested in what we do here at the observatory, again, I highly encourage you to sign up for it on the website listed on the slide. It is free, so don't worry about that. If you are interested in making more of a financial impact with our observatory, we ask that you consider being a patron. Now, Dr. Plavchan and I have great plans in expanding the reach of our observatory, particularly in the outreach spectrum, where we take telescopes or inflatable planetariums all around Northern Virginia so that students who ordinarily would not have the opportunity to utilize such resources do in fact have that opportunity. And of course, this requires manpower, this requires people to man it, and that of course requires financial backing. So there are a few levels at which you can participate, from star all the way up to Big Bang. And just to show you that I do put my money where my mouth is, I am in fact a patron of our observatory. This is not a one-person operation. Dr. Peter Plavchan is the director of our observatory. I am the deputy director. We have two grad students who are with us tonight, Kevin Collins and M. Thunyapong. who are our graduate assistants. They are the ones who are in charge of really maintaining our telescope and also coordinating events such as this and private tours. And we have, and Jonathan is our president of the Friends of the Observatory student organization known as PHOTO. So again, I would encourage you to Google that if you are interested in that particular student organization. We also have Andrew with us today. He is one of our tour guides, undergraduate tour guides, and he will be participating in or leading you through one section of the guided tour this evening. Without further ado, we have William Matzko. He is, again, a third-year PhD student here at George Mason University. He is part of a research group that is led by Dr. Shobita Satrapal, who looks at galaxies, particularly the connection between galaxies and black holes, the supermassive black holes in the center of them. And so today's talk, he is going to be letting us know about active galactic nuclei or potentially colliding galaxies and what impacts that has on those supermassive black holes. So without further ado, take it away, William.
Okay, great. Thank you for that nice introduction, Dr. Park. So let me go ahead and share my screen. So let me full screen that. Okay, so I assume you all can see that.
I can, yes.
Okay, great. So let me go ahead and just set a timer to pace myself, and then I'll get started. So yes, hi, my name is William. As Dr. Park said, my name is William. I'm a third-year PhD student here at GMU. And this talk is going to be loosely based on a paper I recently submitted. But instead of talking about that paper, I more so want to talk about the motivation behind that paper. So why I bothered to carry out that research and why it's important. So to that end, I'll be talking about primarily the winds of galaxies and how these winds can guide a galaxy evolution. So for an outline of the talk, just so you know where this is going to be going, I'll begin with some motivation, so some fundamental questions to the field. And then I'll talk about the necessity of this thing called feedback, and then I'll discuss the common merger paradigm, and it'll be clear what I mean by that soon. Then I'll move on to galactic winds. I'll talk about what I mean by that and their appearance and what's powering them. And finally, I'll discuss the merging environment in winds, which is related to my paper. So I'll examine how the merging environment impacts those galactic winds, if at all. And finally, I'll leave up some conclusions and key takeaways. So I can't think of a better way to begin this talk than by showing you one of my favorite images in all of astronomy. So neither of these are it, but they are related to my favorite image. And in the left image here, I want to turn your attention to the arrow that's labeled UDF, which stands for Ultra Deep Field, better known as the Hubble Ultra Deep Field. So the Hubble Space Telescope is a telescope in space, and it's given us an immense amount of scientific information about the universe. And one of the things it's done for us is image this region of space called the Hubble Ultra Deep Field. So this image was generated between September of 2003 and January of 2004. And it is located southwest of the constellation of Orion in the constellation of Fornax. And this region here is an incredibly small region of space. It is a square of about 2.4 arc minutes on one side. So what's an arc minute? It's just a unit of angular measurement. So we all know that there's 360 degrees in a circle. If we take that circle and we divide it into 360 even pieces, and then we take one of those pieces, then we have 1 degree. If we take that 1 degree and divide it into 60 even pieces again, then we take one of those pieces and we get 1 arc minute. So for reference, the diameter of the full moon is about 30 arc minutes. And on the right here, we have a scale image of the extreme deep field, which isn't quite the same as the ultra deep field, but I couldn't quite find an image like this one on the right for the Hubble ultra deep field. But the two fields are comparable in size. The extreme deep field is a little bit smaller. It's about 80% the size of the ultra deep field. But nonetheless, you can get a sense for the scale of this. And if you want some numbers to it, the Hubble Ultra Deep Field imaged about 1/13 millionth of the sky. So an incredibly small region of space. So Hubble was looking at this region for about 1 million seconds, or about 11.5 days in total. And what's interesting about this region is that there's nothing particularly interesting about it, at least not at face value. It's very dark, it's devoid of light, at least to our eyes. And it just seemed like this very empty void. But nonetheless, we told Hubble to stare at this for 1 million seconds. And what did it do? What kind of data did it see? What things did it see? And that is what we have on this slide. We have the Hubble Ultra Deep Field. From that small region of space, we see this beautiful array of shining jewels in the sky. Virtually every single point of light you see in this image is a galaxy. And these galaxies existed some 13 billion years ago. The light from some of these being generated only about 400 to 800 million years after the Big Bang. So this is one of the deepest views of the universe ever taken. And in this image alone, there are about 10,000 galaxies. And this image is worth more to us than just a nice piece of eye candy. It provides very valuable information about the demographics of galaxies. So for instance, we can see that we have a variety of colors. We have orange colors, we have red colors, we have blue colors that are generally a bit smaller, but we also have some structure to some of these galaxies. So in this one, we have this spiral arm structure emanating from the center, same here, but some of these also kind of look like blobs. So you don't have that spiral arm structure. So a natural question to ask is, how did these galaxies get here? How did they evolve? And the answer isn't exactly known, but we do have some ideas. So based on that last image and other data, we can generally say that there are two overarching categories of galaxies. We have spiral galaxies and we have elliptical galaxies. There are other kinds and you can subdivide them further, but by and large, you have spirals and you have ellipticals. Spiral galaxies are so called because they have spiral arms emanating from their center, like in the image on the left. And these spiral galaxies tend to be younger and bluer and less massive compared to ellipticals. So we know that spirals tend to be younger, and because we know that spirals tend to be younger precisely because they are bluer. So because they're blue, that means there's active star formation going on in those galaxies. So when you're generating a bunch of stars in a galaxy, you will generate a wide variety of stars in different masses and luminosities. Some of those stars will be extremely bright and extremely luminous, and those bright stars are going to be blue. But the trade-off is that those blue stars don't last very long. They die out pretty quickly. And so when you see a bunch of blue in a galaxy, you can infer that it has a bunch of young stars in it. So at the very least, you can infer that there's ongoing star formation in that galaxy. and it's probably a young galaxy. But in contrast, you have elliptical galaxies, and those are more elongated, and they're often called red and dead elliptical galaxies because you don't have star formation. If you did, you would expect to see more traces of blue, but you don't. So a question is, how do we form elliptical galaxies? And we can, or what is the process, so to speak, of spirals going to ellipticals? Is that even the appropriate question to ask? And the answer is yes. We think spirals merge with other spirals to form elliptical galaxies. So that would explain why elliptical galaxies tend to be more massive and older, but that doesn't necessarily explain what happened to the star formation in those galaxies. So something had to have happened to shut off the star formation. And there's a special name to describe that shutting off of star formation, and that is called quenching. So that's an important word. I'll use it multiple times throughout this talk. So quenching is just shutting off star formation. That's all it means. So a key ingredient, or something we think is a key ingredient, is this mysterious thing called feedback or winds. And what I mean by feedback, it's more so a broad general term that simply refers to a process that interacts with gas and dust in a galaxy and regulates its supply. And I'll be a little more precise with that language later. But nonetheless, we know from simulation work that feedback is very important. So there is a genuine motivation to introduce feedback. So one of the ways we can assess our understanding of the universe is to try to simulate it. So these simulations are generally very realistic, and we pour all of our knowledge of physics and astronomy and astrophysics into these simulations, and we try to reproduce observations. And if our simulations agree relatively well with observations, then we can be confident that we have a good understanding of what we are simulating, of what we're trying to figure out. But if our simulations don't match observations very well, then that means we don't understand something. There's a piece of the puzzle that's missing. So simulations using the Lambda cold dark matter model are actually very, very successful on large scales. They can accurately reproduce large scale structures and properties, but they have a little problem with galaxy formation. So that is shown in this figure on the left. We have the what's called the luminosity function, which is a terrible name for it. It should more so be called the luminosity distribution, because this luminosity function tells you, if you give me a luminosity range, I can tell you how many galaxies, the number of galaxies that are expected to exist in a sufficiently large and random sample of the universe. So that's all the luminosity function is telling you, the number of expected galaxies for a given luminosity. So in red here, we have some lambda cold dark matter simulations. And in blue, we have some observations. Now, again, this is a rough sketch, but it illustrates the idea. So at lower luminosities, our simulations overpredict the number of small and faint galaxies. On the other hand, as we go to larger luminosities, we have the same problem. Our simulations predict too many big, bright galaxies. But towards the middle, our observations agree pretty well with the simulations. But we still have this problem at the ends. So how do we fix that? So in order to try and fix that, we need to introduce interactions between normal matter. So it's called baryonic physics, literally just the normal matter in the universe, stuff you find on the periodic table. So we can simulate additionally star formation, feedback, and galaxy mergers. So if we include that, then our simulations can agree better with the observations. So I will discuss that in a moment, but I do want to explain a couple of the labels here, this SN and AGN. So SN stands for supernovae, specifically supernovae feedback. And as we'll see, this can effectively correct the simulations and bring this guy down to what we see with the observations. But this is only efficient in lower luminosity galaxies. Whereas for AGN, AGN feedback is more dominant at higher luminosities. And by AGN, I mean active galactic nuclei. So an active galactic nucleus is simply a supermassive black hole in the center of a galaxy that is actively accreting matter. So this talk isn't unfortunately centered on the physics of AGNs, so to speak. It's focused more on winds. There's just too much to talk about there within 45 minutes. But anyways, let's take a quick look at how feedback can correct this luminosity function. So here on the left, we have a plot of star formation rates in solar masses per year versus the time in billions of years. And we have a variety of feedback models. So in blue, we have no feedback. In red, we have a semi-realistic feedback model. And then in black, we have a very detailed and realistic stellar feedback model. And the key takeaway here is that with no feedback, we have very high star formation rates, about 30 solar masses per year. And for a very detailed, realistic stellar feedback model, that can bump it down to a peak of about less than 10 solar masses per year. So that's going to cut down on the brightness of these galaxies. And here on the right, we have the luminosity function plotted against the absolute G-band magnitude. So this is not exactly the luminosity, but it's basically the same as the luminosity. It's very similar. So with these data points here, these circles, those are observed values of the luminosity function at a given absolute magnitude. And these lines, the solid line and dashed line, are various models of stellar feedback. So we can see that particularly for the stronger types of stellar feedback, the simulation work is in pretty good agreement with the observations. So stellar feedback can fix the luminosity function problem at lower luminosities. So at higher luminosities, we need to look at AGN feedback. So on the left here, we are looking at stellar mass ratios, simulated stellar mass ratios. So we have something called HAGN, and that's just standing for the simulation suite that they used, the Horizon simulation suite, so they call it HAGN. So they're looking at galaxies with AGN and galaxies that don't have an AGN. And then that's on the vertical axis. And then on the horizontal axis, they're looking at the stellar mass of galaxies with AGN. And so what we see here is as we get to larger stellar masses, we get larger and larger quenching of star formation. So, and this holds true for a variety of redshifts. So for small redshifts, like z equals 0.1, that means we're looking at galaxies that are very nearby in the local universe. And at higher redshifts, z of 5, that means we're looking very, very far into the past. But anyways, at these larger masses, we can see that at these redshifts, the star formation quenching we can have an up to 80% reduction in the star formation, but this isn't very effective at smaller masses. And then similarly, on the right here, we just have another plot of the luminosity function against absolute magnitude scaled by some constant factor. Again, we have some diamonds here that represent observations and the solid and dashed lines representing a variety of simulations. So again, we can see that this AGN feedback can fix the problem with the luminosity function at higher luminosities. So we know that feedback is necessary then to bring the Lambda CDM simulations into agreement with observations. So as I discussed earlier, there's a notion of two spiral galaxies merging to form ellipticals. And this I want to revisit that and show a different simulation of that in progress. So we have two blue spiral galaxies starting out, and they will slowly gravitate towards each other. And as they get closer and closer, and they will have a pass through, and as they pass through, the gravitational torques will kick around all of that gas and dust, and it can expel it from the galaxy. And as we get multiple pass-throughs, we can kick out more gas and dust, and eventually the galaxies will coalesce into a single galaxy. So notice it started out as blue spirals and then merged into this more blobby red elliptical galaxy. So how exactly does that happen? Well, we think that there is something called an outflow or galaxy wind that's happening to cause that. So as this gas and dust was getting kicked out of the galaxy, that is called an outflow. And if that gas can escape the galaxy, then that is gas that is no longer going into the creation of stars. So that could potentially shut off star formation and lead to quenching. But this is just an idea. There's no direct evidence of outflows causing immediate quenching yet. And there's also a possibility that when you expel that gas and dust from a galaxy, you can shock a previously undisturbed material in the galaxy, and that can actually trigger star formation. So it's not entirely, so the picture isn't entirely clear, but we do know that some kind of feedback is absolutely necessary based on what we just saw. So this leads me to the definition of a wind. So a galactic wind or an outflow, I'll use them interchangeably, they're pretty much the same thing, is simply gas and dust that has been ejected from a galaxy by one way or another. And I'll talk about how it can actually be ejected a little later. So these winds are complex. They're seen in every wavelength regime from the radio to the optical to the infrared to the X-ray, and they're seen in various phases of the interstellar medium, meaning that we can see them in molecules, we can see them in neutral atomic atoms, we can see them in ionized and highly ionized atoms as well. And these outflows can extend from parsec to kiloparsec scales, so they can be very significant in size, comparable to the size of a galaxy. So in this table here on the left, this is just a brief summary of various gas phases and what you can use to study that phase. So in particular, my work is focused on the ionized gas phase, and I use the O3 line to study that. So this O3 is just an oxygen atom that's been ionized twice, so it's had 2 electrons kicked out of it. And another thing that's really amazing to point out is just the sheer power of these outflows, and that's illustrated in the figure on the right. So we have a plot of the AGN luminosity on the vertical axis, and on the horizontal, we have the maximum outflow velocity. So blue here is corresponding to molecular gas, Green is corresponding to ionized gas. Don't worry about these gray data points. And then the red is corresponding to the highly ionized gas in the X-rays. And we can see here that the ionized gas can have very significant outflow velocities up to 0.3% of the speed of light, which is incredibly fast. But the X-ray winds can be even faster, and they can be as much as about 33% of the speed of light, which is absolutely ridiculously fast. So you have these gas particles and whatnot that's being accelerated to extremely high speeds in these galaxies, producing these extremely powerful winds. So you can probably guess based on this table and this figure, we actually know that these winds exist. So we have observational evidence of these winds here. And here's just a handful. So we have one, NGC 3079, imaged by the Hubble Space Telescope. So we can see that we have an outflow in the central region of that galaxy. Then we have M82, also known as the Cigar Galaxy, again imaged by the Hubble Space Telescope. And we have this red plume that is being ejected from the galaxy. That red plume is ionized hydrogen, and that is an outflow. And then finally, on the right here, we have a very interesting system. This is actually a dual supermassive black hole system. So this is a merger system. And in here, you have two outflows. You have one that is traced by O3, which is driven by an AGN. And then you have another one that's traced by H alpha, which is driven by stellar activity. So we do have images of these outflows. And based on these images, we can kind of model their general shape. So, and these outflowing winds tend to take on what's called a biconical shape, or somewhat like an hourglass. So in the figure on the left here, our line of sight is off to the left. So this is how we're looking at the system. We have a dust plane right here, which simulates the disk of a galaxy. And then we have this outflow here, this wind here. And that wind is again in the shape this wind is again in the shape of this bicone. So you have part of that wind that is coming towards us. So that's going to make the wind blue shifted. And then you have part of the wind that is going away from us. So that's going to make the wind red shifted. And as this will actually have some important consequences for how we observe some of these winds, and I'll mention more of that later. But on the right here, in the middle and in the figure on the right, we just have some more observations of a biconical outflow. So we're looking at the flux of H alpha in NGC 5728. And we can see that this again traces out a bicone shape. And if we look at the velocity of that gas, we can see that part of that gas is coming towards us. So the blue gas here, and then part of that gas is going away from us. So the red gas here. So again, that's consistent with this biconical shape from an outflow. So earlier, I mentioned about the powering of these winds. So in this one, I said that you had an AGN-driven outflow, and then you had one that's driven by stellar activity. So there's a couple ways you can, or at least a couple ways you can generate these winds. And the details aren't entirely known, but we do have ideas. So you can power winds, either you can power these outflows or galactic winds from smaller stellar winds or supernovae. And you can do that just by imparting mechanical energy and momentum into the surrounding gas and dust. So these stellar winds are only important in younger galaxies with a lot of high mass stars. Otherwise, supernovae tend to be the dominant driving mechanism of winds. On the other hand, we have black holes, which are ubiquitous in galaxy centers. And there's a whole fascinating topic here to talk about, but I don't have time to go into it. But those black holes may be accreting matter, and those accreting black holes are called AGN. And so we can potentially power those winds via accretion. So radiation from that accretion will push on the surrounding gas and dust to drive those winds. And that's mostly seen in high luminosity AGN. AGN can also generate extreme magnetic fields, and those also probably play a role in powering and collimating the winds as well. So again, the details aren't very known, but we do have some loose idea of how this stuff is physically powered. So again, we just have some examples here. So on the left, we again have M82, which is an outflow driven by stellar activity. And then on the right here, we have an AGN-powered outflow in NGC 7582. And they were using O3 to trace that outflow. And again, it's looking like a bicone shape here. So this is kind of the background I wanted to provide here. So let's give a quick recap, and then I'll introduce my specific research question. So we want to know how galaxies form and evolve. So we know that spiral galaxies tend to be younger and bluer and less massive compared to ellipticals. And we believe that spirals can merge and form ellipticals. That explains some of the properties of ellipticals, but it doesn't really explain why the star formation is turned off. It doesn't explain why that star formation is quenched. So we know that this thing called feedback or winds exist, and they are necessary to make our simulations agree with observations. And these winds or outflows are thought to play a role by expelling gas and dust from a galaxy. So you are just depriving the galaxy of the raw material needed to generate stars. And those winds can be powered either by stellar activity, so winds or supernovae, or AGN via accretion activity. So I didn't get to talk about this a whole lot during the talk, but mergers are thought to play a very important role in other aspects of galaxy evolution. In particular, mergers can trigger AGN. So as galaxies get closer and closer together and further along in their merger, there's enhanced gravitational torques on the system that will funnel gas inwards towards the supermassive black hole, and you can get an accretion disk that way. You can also get elevated star formation rates in late stage mergers, and those mergers can also drive morphological change. However, it's completely unknown how the merging environment impacts winds, and that is my research question. How does the merging environment impact these winds? And you need to be very careful with how you want to answer that question. So you need a large merger sample, and you need a very robust control sample that consists of isolated galaxies that have similar properties to your merger galaxies, because you want to specifically isolate what's happening in the merging environment of that galaxy, of those systems. So no one has explored this before in a systematic way, but people have looked at outflows and winds in merging systems, but they haven't done this. They haven't compared it to a control sample of isolated galaxies. So how exactly am I kind of constructing this sample? What am I doing to answer this question? So I'm using data from the Sloan Digital Sky Survey, which is a 2.5 meter telescope located in New Mexico. It is focused in optical wavelengths, so about 3,600 angstroms to about 10,000 angstroms. For reference, the human eye is sensitive to light, visible light, around 4,000 angstroms, which is blue light, to about 7,000 angstroms, which is red light, and green light's around 5,000 angstroms or so. So the Sloan Digital Sky Survey has surveyed about 1/3 of the sky, and it has taken observations of over 4 million objects. And what's really interesting is that all this data is available online, free to access. So you can go to their website, stss.org/their DR16, their latest data release, and you can just look at galaxies and you can see their spectra and their properties. So the images here are just on the right here, we have a picture of the Sloan Digital Sky Survey itself. And SDSS uses a series of plates and fibers. So it's literal plates like what we see here in the middle image, and fibers. So in this middle image here, we have a plate with holes in it. And each of these holes at one point had a fiber going through it. And that fiber was placed such that it was observing some kind of star or galaxy. So you would have this plate in the telescope, and then you would just punch out all of these holes corresponding to targets you wanted to observe, and then you would connect these fibers to it. And that's how you would get your data. So that's just a cool tidbit of information there. But anyways, let me talk about my sample and how I'm looking at mergers and my isolated control galaxies. So I have a sample of about 4,000 galaxies that are currently undergoing mergers. They are at various stages of their mergers. Some are fairly far along, some are much more further apart. You can see those in this bottom left panel here. These are some of the closer in mergers. And then we also have about 250 post-merger galaxies, meaning that you have nuclei that have properly coalesced into a post-merger state. And you can see those here in the middle image. So the pairs and the post-mergers contain both AGN galaxies and galaxies that are dominated by star formation. And these mergers, we're looking at major mergers. So galaxies that are of roughly comparable size to each other. And we're also looking at objects in the local universe, so low redshift. And then we have a control sample of isolated galaxies that have similar properties to these mergers. So they have very similar mass, they have similar redshift, they have similar luminosity, and so forth. And you can see some of those here on the right in this strip. So those are the isolated control galaxies. So we need to figure out outflows. We need to see outflows in these spectra, and the resolution of SDSS does not let us do that, at least not in the sense that we see it like in Hubble with these images here. Instead, we look at the spectrum of an object, and that looks something like this. So it is simply a plot of the flux, the light that we receive from an object versus the wavelength of that light. So this on the bottom left is an example of a spectrum of a given object in my sample. And we have this base level that is the stellar continuum, and the noise, so this is the stellar continuum, which is just all of the starlight from a galaxy. And this noise in this stellar continuum isn't actually noise, it's actually various absorption features in the stars in that galaxy. But peeking out above this continuum, we have these big lines here, and those are called emission lines, and that's just various gas from a galaxy that has been excited and is now giving off light. So as I said earlier, we're using a particular emission line, the 035007 line, to examine wind signatures. The reason we're doing that is because this line it's common in the sample, and it's also fairly bright as well. So earlier I said that we generally model outflows as a bicone in shape, and that has a very important consequence. So if we look at a line profile, if we look at the emission lines, then if we have an outflowing component, then we expect that outflowing component to, or that wind to be blue shifted. So it's going to have this asymmetrical feature to it. The reason we don't see this red shifted component is that the galaxy disk is too dusty to see through. Typically, it's too dusty to see through. So we're only seeing this component of the wind that's coming towards us. And so that's going to be blue shifted, and we're going to get this blueward asymmetry in the emission line profile. So that's great. We have this, we know what we're looking for in the spectrum of a galaxy. So, another reason this line is useful is that it's also not very crowded in this area. So you don't have to worry about multiple lines being blended together. So this is a nice, generally lonesome line. So what we need to do is we need to come up with a fit to these lines. So we need to, like how you would fit a line to data. Well, we need to do that, except it's a little more complicated than fitting a line. So we need to fit the continuum, and we need to have fits to the emission line. And generally, without going into too much detail, you want to model these emission lines with two components. One will model the core of the line, and the other is going to model this blue asymmetry. And we do that using a custom Python code. It's called Bayesian AGN Decomposition Analysis for SDSS Spectra. For short, it's called BADAS. And we have a fit to the same spectra here. And so you can see, sorry that this is kind of cut off at the bottom. We have this blue component here that's modeling the core of the emission line. And then we have this purple, we have this purple component that is modeling the asymmetrical part of the line. And so we can look at this asymmetrical, this purple component to extract information about the outflow. So here are a couple other examples. In the top one, we have an outflow here that is pretty clear. So we have this very broad, low outflowing component. Then we also have a bad fit to H beta over here, but don't worry about that. That doesn't impact anything. And then in the bottom here, we actually have a spectrum that does not have an outflow. So this line is actually pretty symmetrical. So there's no justification to fit an outflowing component to that guy. So not all of the galaxies in this sample will show a wind or an outflow. So I've basically fit all of these galaxies, all of these mergers and controls, and I've calculated how common these outflows are. So the outflow incidence rates, I've calculated outflow velocities and so forth. And I'd like to share a couple of these results. So the first one here on the left, we have the merger sample of galaxies, and then on the right, we have the control sample. So let me explain the legend here. So the green data points are galaxies dominated by star formation, and then KO3 and KO1, those are optically selected AGN. So without going into too much detail there, you can think of KO3 as being dominated by AGN, but it can still have some contribution from star formation, whereas KO1 AGN are wholly dominated by AGN. So it's KO1 can be thought of as a purer AGN than KO3. And then finally, we have this WISE plus BPT sample, and that means that we have infrared selected AGN, so it has to have a sufficiently red color, and it's called WISE because we're using the WISE survey, which is an infrared telescope, to to make that infrared AGN detection. And then BPT, that just stands for optical AGN. So we're requiring not only a KO1 or KO3 AGN, but we're also requiring an infrared detection for that AGN as well. So as we go up this list, we have more stringent requirements for an AGN. And we can see here that we have a plot of the outflow fraction in a given luminosity bin. So we're looking at how the outflow fraction changes as we change the luminosity. And at these lower luminosities here, we don't get anything. We have pretty much no outflows whatsoever in any of our sample. And as we go to higher luminosities, these outflows become more common with rates of around 60% at the highest O3 luminosity bins. So another thing to note is that these star-forming galaxies, they systematically have a much lower incidence of outflows or galaxy winds at every single luminosity. This is also echoed in the control sample as well. So in particular, we see something interesting here. The WISE plus BPT AGN at the highest luminosity have a very large number of outflows compared to the optical AGN. So you could have, so there could be something special about this sample here of infrared selected AGN. Special as in it's easier to generate powerful outflows in that sample for whatever reason. So the other part, or the main question I was trying to answer with that work is how galaxies or how these outflows or winds change as galaxies progress in their merger. And the answer is that the merging environment essentially doesn't have any impact on these outflowing winds. So that's illustrated with these plots here. So we're looking at the outflow incidence as a function of the projected separation. So just how far these galaxies appear apart on the sky. So we can see that there's pretty much no difference between the mergers and the controls for any of the samples here. And there's also no general kind of trend as we go from higher separations to smaller separations. So it doesn't seem that, so if we control for the power source of the outflow, then it doesn't seem like the merging environment gives us anything extra. So finally, we can look at the outflow velocity. Again, on the left, we have the merger sample, and on the right, we have the control sample. And this W80 is just one way to measure outflow velocities. But again, we see that star-forming galaxies have weaker outflows with velocities only around 200 to 300 kilometers per second, while the AGN have much higher outflow velocities of 600 kilometers per second all the way up to about 900 kilometers per second. And again, in the control sample, it's a very similar story. So we do have higher, of course, higher outflow velocities and higher luminosity AGN as well. So the main quick conclusions from the work that I've done here are that when we control for the power source of the outflow, the merging environment doesn't have any further impact on ionized outflows. We can also see that the presence of an AGN is needed to drive powerful winds, and there is some dependence seen on AGN selection techniques. So outflows tend to be more common in the WISE plus BPT AGN, and then in the KO3 AGN, they are not as common. The average incidence there is only around 7%, whereas in the KO1 AGN, the incidence is a bit higher, around 14%. So the presence of an AGN is probably needed to drive powerful outflows. And finally, outflows are only present in sufficiently high luminosity galaxies. So the general key takeaways from this work, or this talk, I should say, is that we don't fully understand how galaxies form and evolve. We know that winds and outflows are necessary to produce accurate simulations, but we don't know how exactly those outflows can quench star formation in a realistic scenario. So they may be responsible for quenching star formation, but we don't have a smoking gun observation of that. We don't have direct evidence of that yet. And finally, it seems that from my work, it seems that merging environments don't seem to have a significant impact on outflow properties. So that is my talk. Sorry I went a little bit over, but that's everything. So I see there's a lot of chat comments here, so I can take any questions. So thank you for listening.
Can't seem to find my controls to actually unmute myself. So, well, or at least show my picture. So, there we go. Now I found it. So if we could all give a virtual round of applause to our speaker. Thank you, Will, for a very engaging talk on AGNs. I certainly enjoyed it. If anyone has any questions for Will about his presentation or just AGN in general, please feel free to answer or ask those questions in the chat. I'm going to take the presenter's prerogative and ask the first question. I don't know if this is quite related to your work, but I know from my experience with an AGN group at Georgia State, which my alma mater, one of the open questions was whether or not there is a true spectrum of mass for the supermassive black hole at the center of the galaxies of these AGN. So I was wondering if your research could inform on that question, whether or not is there a truly for like smaller galaxies, are there smaller and smaller supermassive black holes, or does it actually cut off at some mass limit? And the reason why I asked this is I noticed you were talking about outflows seem to shut off at the lower luminosity end.
Right. So your question is for these supermassive black holes at the centers of galaxies, you're asking what about the distribution of those masses? Is there some upper limit or is there some lower limit? Is that?
Yeah, if there's a lower limit, and whether or not this outflow research can answer that question, or at least inform onto the answer of that question.
So as for whether or not the outflow and winds can answer that, I don't think that's necessarily the right way to go about answering that particular question. You could find some loose connection, but there are better ways of approaching that. So there are kind of lower limits to the masses that you observe in these in supermassive black holes. So we have observational evidence for stellar mass black holes. We know those exist, and then we have evidence for supermassive black holes, which are about on the order of 1 million times the mass of the sun. But there's a very wide range of masses that are kind of missing, and those are called intermediate mass black holes. And someone in my research group, Jenna Kan, was working on that topic, so she is far more knowledgeable about this than I am. But these intermediate mass black holes, we're searching for those. They are expected to exist, particularly in smaller dwarf galaxies. But as far as I'm aware, there hasn't been a smoking gun evidence for the detection of intermediate mass black holes. I think there's been hints that intermediate mass black holes do exist in galaxies, but I'm not fully up to date on all the status of that. So to answer your question, yes, there is a lower limit to these supermassive black holes that we typically see in galaxies. It's around, it's on the order of 1 million solar masses or so. And below that, you're looking for elusive intermediate mass black holes.
Okay. Well, thank you. We do have a couple of questions from our audience. From Christopher, he asked, I have a question about space wind. Are we able to see how we can correlate space wind we find and see if it is from the time from the Big Bang?
Okay, so I think I see what you're asking here. So the winds that we see in galaxies, they're not going to be that old. So they can only be as old as the galaxy itself. And it takes time for these winds to develop in the galaxies. So if you have even like what I showed earlier with in the Hubble Deep Field, you have those very young galaxies just after the creation, or formed shortly after the Big Bang. Those, if you do manage to find outflows in there, they're probably not going to be, left over from the time of the Big Bang. They have to be, you have to wait for those outflows to form. So yeah, you're not gonna see any correlations there.
Okay. Next question we have is from Farhan. Nope, wrong question. Ahmed. What is your speculation about the future of this topic, especially with the general access to JWST? And actually, that was a question I was thinking about while you're giving your presentation.
Yeah, so that's a very great question. There's a lot of promise for JWST to look at outflows in the infrared. So you have unprecedented sensitivity with JWST, and while you can, like I showed earlier, you can spatially resolve outflows from the ground. With JWST, you'll be able to get much clearer pictures from that. Of these outflows in general. So you'll be able to do a whole lot more. You can constrain the energetics of the outflows a lot better. So one thing I didn't really talk about here was stuff like mass outflow rates. So how much mass is being ejected in those outflows, and how does that compare to the current star formation rate in the galaxy? So that's something referred to as the mass loading factor. So it can quantify how efficient the quenching is. And with the spectra I have here, I can't do that. I don't have the spatial resolution, but even when you do have sufficient instrumentation to do that, it's still very hard because there's a lot of uncertainties and parameters are poorly constrained. So JWST can help constrain those unknown parameters and can lead to more accurate pictures on feedback and winds. So that's a general take on that.
Excellent. Well, since we're past 8 o'clock at this point, unless there are any final questions, I'm going to hand it off to Kevin and Andrew and to give a telescope tour of our observatory.
Great, thank you. Yeah.
All right. So yeah, thank you again, Will. And yeah, so on to Kevin and Andrew.
Okay, give me just a moment to share. All right, we should be looking at a set of webcams now. All right, welcome everybody. Thanks for coming to our final evening under the stars of the semester. I want to start off by thanking William for your talk. And also, I would like to go ahead and preemptively invite everybody back for the fall. We may potentially by then be doing these in person, in which case, after our talk, you'd be able to come up to the observatory in person, and maybe if the weather's nice, get a look through the eyepiece, which will be just a completely different experience that I would highly recommend. So now welcome to the GMU Observatory. As was mentioned at the beginning, we're at the roof of Research Hall that we're looking at through these cameras right now. You can see the actual dome. You might notice it if you're walking past Research Hall, but it's up there on the roof. It's about 20 feet across or so for reference. And you can see we have this dome. It rotates a full 360 degrees, and it has a shutter, which we open and close to actually look out at the night sky. And we do so using our main telescope, this 32-inch reflecting telescope. Sorry. And we can control this telescope remotely, as I'm doing right now. You can see our control room on the roof of Research Hall is currently empty, and I'm remotely logged in to the computer there on the desk on the far left-hand side. So up until the summer of 2020, this is where a lot of astronomy research students would be spending long nights gathering data. But now we have the luxury of being able to do that from the comfort of our own homes. So we can control our observatory using a variety of software on this control room desktop. I'm going to use one right now. This is called the Skyx. We use it to move and point the telescope itself. And so I can connect to it, and we have this night sky view. This is basically whatever the current night sky looks like. And it's a relatively simple point and click interface where I can point to a location and I can tell the telescope to go there. And acting a little bit slowly. As I tell it to, if we go back to the camera, we will see the telescope begin to point in our direction. So this telescope, I mentioned it before, it's a reflecting telescope. The actual optical design is called a Ritchie-Chrétien Cassegrain reflecting telescope. Now, all of those words essentially just they describe the optical design of the telescope, the path the light takes to reach from the sky to your eyes or the camera or whatever instrument we have on the very back. So with this particular type of telescope, the light obviously will be coming in from the sky, and it enters through the front of the tube here that's coming into view. It then bounces off the primary mirror at the back of the telescope, which is 32 inches across. That's also called the aperture. It's essentially just the main light collecting area of the telescope. Let me actually move this a bit further down and over so we can actually see the primary mirror. Oh, wrong direction, sorry. Let's try like that. So after the light bounces off that primary mirror in the back, it gets reflected back out of the tube. But it gets focused by the primary mirror. And why aren't we pointing at the screen? Okay, and that focused light hits this other smaller mirror called secondary mirror here at the front end. You can see that middle circle there that's about a foot across, and that focuses the light from the primary mirror back down the middle of the tube. So the primary mirror has a small hole in it, and so all of the light that's collected goes through that small hole in towards the back of the telescope before it's reflected one more time, either into an eyepiece if we're looking through it in person, just kind of like a backyard telescope, or to one of our instruments or cameras if we're taking research data or viewing things remotely. So, hold on a second. We're not quite low enough for the primary mirror to be in view. I'm going to move it down just a little bit further so that we can just see the edge of that primary mirror. There it is, perfect. All right, so that's enough about the optical design of the telescope. Generally, we would use our CCD camera for when we're not there in person. And it essentially just counts photons, the rays of light that hit our detector. It counts those up to give us an image. And it has a field of view of about 26 arc minutes, as referenced in William's talk earlier. An arc minute is 1/60th of a degree. So 26 arc minutes on a side is about a half a degree. It's a little bit smaller. And for reference, when looking up at the sky, the moon is about 31 arc minutes, about half a degree. So our research camera covers about the same portion of the sky as the moon takes up, just a little bit smaller. So when we're using this telescope, we're looking at a pretty small region of the sky overall. Our telescope gets used for a variety of functions. Obviously, there's events like this, public nights, and we do tours for introductory astronomy labs and also private tours to the public for those that are interested in. We also, as was mentioned at the beginning, we have our student organization, PHOTO, Friends of the Observatory, who every several weeks or so are able to come up onto the roof and use the telescope for astrophotography and kind of fun, just looking at things that are interesting. And then finally, we use the telescope for research on every clear night after all of those other things are done. So the primary research we do with the telescope is looking for exoplanets, or planets around stars other than our sun. And we have been successful in helping locate a decent number of planets at this point. All right, so now that we've been acquainted with the telescope and some of the, I guess, facts and figures about it, I will turn it over to Em and then Andrew, who will show us some of the interesting objects we've been able to capture images of using the campus telescope.
All right. Okay, so let me take over the computer screen. So since we do the closed dome tour, you can see the cloud this evening is pretty thick. We cannot open the dome and capture the real images of the night sky, but luckily we do have some saved images that we can show you tonight. Let's first go with the galaxies. Some galaxies, okay. We have some images captured by this telescope in colors. So usually if we use the CCD camera, it will produce monotonic images like this because it can only record the image with a specific filter. Maybe it's a red, it's in green or blue, or maybe in infrared or UV light. And like Kevin just mentioned, the CCD camera will only record the intensity of that images. And we will just adjust the correlation of that intensity to black and white like this. So to have a nice images like this kind of color images, we are required to have multiple images combined. So the first images that I want to show you is this Bose Galaxy, or M81. It's in the Ursa Major constellation. I can give you an idea how to spot this on night sky. We use this software called Stellarium. So it's Bose Galaxy. Oops. This software can mimic the night sky. So this is the ideal night sky that we should see if there were no clouds today. So this object is around this region. We cannot actually see it with our naked eye. We have to use telescope because it's pretty faint. Its magnitude is about 6, shown here. The object itself, the galaxy, is about 25 million light years away. Let me switch the screen back to our image. Okay. So this both galaxies, or the other name is given is M81. M is stand for Messier catalog, named after Charles Messier, a guy who invented this catalog of some astronomy objects. This galaxy is spiral, but it's close to the galaxy called M82, which is also called Skyx Galaxy. And I think we also have that image of Skyx Galaxy. I'm not sure we can actually see it from here. We actually have our image of Skyx Galaxy on this side of the wall, but unfortunately, we cannot see from the camera. So this is the nearby galaxy called Skyx Galaxy. You may be familiar with this because it's also in the presentation that William just given you an hour ago. It's known to have to host several newborn stars. We call it Starburst Galaxy. We suspect it's because the tidal force or the gravitational pull of the nearby galaxy, the Bose Galaxy, because they are so close, so it has interaction inside the galaxy and cause star formation. And I think I can also show you the location of this galaxy on the night sky. Let's search M82. So, yeah, I should just zoom in. Yeah, they are actually close together on this side of the Ursa Major. Sorry, I have trouble switching screen with this software. Okay. We have some information about the image of this Skyx galaxy. As you see, the name is BVR. So that the combination of blue, we call it visual or sometimes called vision. I'm not sure, but the color is about the green color and the red color. So with these three images combined, we create the color image like this. Another color image of this Skyx galaxy is this one, hydrogen alpha, RB, and visual. So it's basically the color is similar. The hydrogen alpha is another type of filter that lies at the wavelength of the specific wavelength that produced by hydrogen. So we can see a slight different component, of Skyx galaxy. But if we do have an X-ray telescope on our campus, but we cannot have that on the Earth, for sure, the X-ray gets absorbed or passed through the telescope very easily. We have to have the telescope on the space for X-ray. But if we do have X-ray telescope for pointing at this object, we should be able to see some pulsars. And there are several pulsars known to located at this object, the Skyx galaxy, and also supernovae, and some weird pulsar that we don't have a full explanation of how it should happen. We named it micropulsar. It may be caused from some object like neutron stars or like massive star in binary system, but we don't know the mechanism. We also have this image of both galaxy. This is recorded by a student organization called Photo, Friends of the Observatory. The image is recorded in red, blue, and visual. Okay. Another group of objects that I want to show you is Whirlpool Galaxy. So this is what I showed you earlier, the monotonic image, but we don't have the information in the file name, so I cannot really tell you which filter we recorded this image. But with some combination and some specifying color filter, we can produce a color image like this. And we can see this Whirlpool Galaxy. It's called M100. M100, oh no, sorry, it's M51. So this group of galaxies composed of two galaxies. You can see this is the bigger galaxy and this one is the smaller galaxy. They are actually merging to one galaxy, and as we expect, they will eventually become somewhat elliptical. But right now we classify it as irregular shape, or maybe it's a spiral, but on the verge to irregular shape. The name of this object is called M51A and B. So the A is the larger one, and the B is the smaller one. It lies on the constellation Canis Venasticide. Let me show you how where it locates. So not far from the Bose and Sika galaxies. Here are the Whirlpool galaxies. We can, for this object, it's bright enough to be spot on some binoculars in very clear and dark night. If you're outside on some clear and dark night and you face to somewhat north, okay, and if you can find the Big Dipper or the constellation Ursa Major, it's on about the tail of this Big Dipper. Okay. You can actually see this on binocular and at least see that they have composed of two combining galaxies. Okay. So Whirlpool Galaxy is not that far, not as far as Bose and Sika Galaxy. It's actually halfway of Bose and Sika's galaxy. It's about 12 million light years from us. Still far, though we cannot actually go there. It's thought to have supermassive black hole at the core of this galaxy. And I think I will pass it over to Andrew now. He also has some objects that he'd like to show you.
Hello, everyone. I hope my voice is not too echoey, but my name is Andrew. I will be your final tour guide to give you a tour on the Whirlpool Galaxy. And just in the interest, or I'm sorry, the Andromeda Galaxy. And just in the interest of time, that's the only galaxy I'll kind of talk about tonight. Hopefully a little bit more in depth, just because it's just one object. So I'm going to pull up an image of Andromeda. A couple images that we have taken, hopefully. Thought we had more images of Andromeda. Well, I guess I'll talk a little bit about Andromeda first. You can kind of imagine what it looks like because it is a Whirlpool galaxy. And at some point, to an extent, all Whirlpool galaxies look pretty similar. If someone could find me the Andromeda Galaxy image, if we have any, that'd be great. But in the meantime, I'll talk about Andromeda. So it's about 2.5 million light years from Earth. And what we do know so far up until now, I should say it was once thought that it was about twice the size of the Milky Way galaxy, but there's been recent estimates that suggest that we were actually pretty off. So in 2019, there was some research done using a combination of the Hubble telescope and the Gaia telescope, which is another telescope that was launched by the European Space Agency that specializes in astrometry, so just measuring distances between large objects in space. What happened was it was measuring some large objects in Andromeda and was able to figure out not only the velocity in which a lot of these objects are coming towards us, but also the not just the radial velocity, I guess I should say, but also the velocity in which it is moving sideways. And based on that, there was a different estimate for the mass of the entire galaxy that came up. And now it's estimated that the Andromeda Galaxy and the Milky Way Galaxy is actually more similar in mass, at least. originally it was estimated to have about twice the amount of stars as our galaxy. So Andromeda was originally estimated to have about 100 trillion stars or so, but now it's a little bit close to around 800 billion, according to those estimates. And the speed in which it's coming towards us is also a little bit different as a result. So there might be a more sooner time for it to collide with our galaxy, as opposed to 4.5 billion years as original estimates stated. But for large galaxies like Andromeda and other galaxies, we do know that there's a tremendous amount of mass in dark matter. Actually, what makes Andromeda Galaxy pretty awesome is that it's so large and so massive that it also has an estimated large halo of dark matter that also contributes to its mass that extends way out past the actual visible borders you see here in images such as these. And to clear up a little bit of information, dark matter is something that we aren't 100% sure of what it is yet. It could be something physical or something that exists that doesn't interact with baryonic matter, which, as William mentioned earlier, is matter that we are made of, that is detectable and interactable. Or it could just be gravity itself that behaves differently on larger scales or on smaller scales. We're not really quite sure yet, but there is some kind of unknown amount of matter that always has to be considered for galaxies, our galaxy and any other galaxy, that has to be, this information has to be, it has to be taken through implications in other ways, such as the speed in which some objects move, how fast they're receding or coming towards us, redshift, blue shift, etc. Especially for very large objects like star clusters and extending out all the way to things the size of galaxies. So, but that is not 100% confirmed yet. So you will find a lot of information online. We'll still place Andromeda Galaxy as like twice as large, 2.5 million light years away. But these studies are from 2018 and 2019. So that has, that is in the process of being updated or further studied. How are we doing on time?
I think you can click on the button at the row below the window.
As for time, it's about time now. If you have,
it's about time. Okay. All right, then I will just stop there then.
Okay.
So if anybody has any questions on that, you can ask or just raise your hand or put it in the comments. All right. So thank you.
All right. If there are no other questions, then thank you all for coming. And as I believe Kevin said earlier, we invite you all to come back next semester so that you might actually get a chance to look through the eyepiece of our telescope and enjoy it in that way. All right. Good night, all. Have a good weekend.
A good one.
Thank you.
All right. Good night, everyone.